Okay, let's pick up with graph connectivity. Um, and this is from the McAllister slides supplemental again. So if you remember graph connectiveness, a connected graph is one which every vertex can be reached eventually by every other vertex. And so suppose you were looking at an airline, looking at flight paths. The connectivity says, can we get there from here? Can I drive to Hawaii by car? Well, no. If we can reach all the cities from all the others in a set of flights, then we have a connected graph. So the spanning tree tells us a set of all flights that connect all the cities. This is a spanning tree. Shortest path tells us the least costly. And so again, like we said before, a graph is connected if every vertex can be reached from every other vertex. This version says that we ignore the directions in a digraph. And so they introduced the term strongly connected to say that it can be connected when edge direction is considered. So this is an example of a graph that's not connected. It's called disjoint. So we could for an undirected graph, perform a depth first traversal or a breadth first traversal beginning at any vertex and verify that you visited all the vertices. For a directed graph, a digraph, we would have to perform a depth first traversal or breadth first traversal beginning at each of the vertices and verify that in each traversal all the vertices could be visited. So that's not very, that's a huge order, big O notation to do that. So we want to use a simpler algorithm, and there is an algorithm called Warshall's, which determines which vertices are connected in an unconnected digraph. So Warshall's uses the transitive property of math. If A equals B and B equals C, then A equals C. And so the same thing if there's a path from X to Y and a path from Y to Z, then there's also a path eventually from X to Z. So we generate the transitive, what's called the transitive closure matrix T, capital T, which contains a 1 in T if there's a path from VI to VJ. So here's the adjacency matrix, here's the transitive closure matrix. So in a digraph, node 2 is not connected because once we get there, we're done. So we're not going to go through in detail the Warshall's algorithm, but there is code in a minute. So for each vertex B, determine, that's the red one, determine every vertex C that can be reached from B. And then for every vertex A, if there's a path from A to B, add a path from A to C through B. So here's the algorithm for implementing Warshall's, just 3 nested for loops and some if statements down underneath the for loops. And once again, we're not going to go through that in detail. So the next thing to talk about is spanning trees. A spanning tree, we briefly saw it earlier. A spanning tree is a set of vertices and a subset of edges, all the vertices and a subset of edges, such that the graph is connected so every vertex can be reached from every other vertex. So there are no cycles in a spanning tree. So every undirected connected graph has at least one spanning tree. And if it's weighted, it has one minimum spanning tree. That's if there may be several minimum spanning trees if some of the edges are equally weighted. So how do you determine a graph spanning tree? Well, you perform a depth first traversal beginning at any vertex, record the edge, and push it onto the stack once it's pushed onto the stack. And since only the vertices are pushed on the stack once, only one edge to each vertex will be recorded. And so record the recorded edges are edges of the spanning tree. So here's Prim's algorithm, and we'll go through a graph in a minute, which will make it very clear to you. Here's the code for Prim's algorithm. So let's say we have this weighted graph of our favorite graph. So we can begin prims at any vertex. So we're going to probably start at 0. And here's the process. You place any vertex into the minimum spanning tree, otherwise known as the MST, and consider all the edges not currently in the tree from all the vertices that are currently in the tree, and add the edge with the minimum weight that's incident to the vertex in the tree, and then repeat steps 2 and 3. So here's a graphic of it. If we start at 0 and the blue nodes are added to the minimum spanning tree, the dotted red edges are considered. So we're going to go from step 1 to step 2. Now we have 0 in the minimum spanning tree. We're considering these 3 edges. We pick the minimum one, which is 5. We add it. So here's 0 and 4 are now, plus the edge between them 5, weight 5, is in the minimum spanning tree. Then we consider all the other edges, 2, 9, and 8 in this example. And of course 2 is the minimum, so that's the one we include. And now we can reach 3 via 4. So we don't want to include, we want to de-include edge 9. And then 3, and then the last one is easy. It's just a single edge. So this is the minimum spanning tree for this graph. And there's something that looks very much like the adjacency matrix. It is an adjacency matrix for the minimum spanning tree. So here's the code, the pseudocode for Prim's algorithm, pretty close to Java. And let's say we had this set of cities that are represented as vertices, 0 being one of them. And we have some flights, and this airline, being cheap, wants to minimize the number of flights so that they can still claim that they arrive at all the airports, but there are a lot of connections. Now, nobody who flies likes connections, but that's the breaks. So there's the description. Here are 3 possible spanning trees. One way to do it is to look at each of the spanning trees and compute the cost. Now so 6 plus 2 plus 5 plus 8 plus 7 plus 5 is probably 33, 28 and 25. So this one at the lower center is the minimum spanning tree because it has the minimum cost. So if we use prims to search this graph, we will find the minimum spanning tree. So we start at 0. And now, unfortunately, they changed the visualization. So the red, solid red are those being considered, and dotted lines are those that are in the spanning tree. So among 6, 2, and 5, 2 is the minimum. So 3 is in the minimum spanning tree. So edge weight 2 is in the minimum spanning tree. Here's a notation for it. You may want to use this in your graph algorithm, in your graph lab. V of t are the node numbers, in this case numbers that are included in the tree, and the edge 0, 3 surrounded by parentheses is the edge that goes from 0 to 3 or 3 to 0. So now we consider 8, 6, and 5, and we choose 5. And then we look at 5, 7, 8, and 6, and we choose 5 again. Now we eliminate edge 6 because now that we have a possible shorter path to 1 than going from 0 to 6. And that's the one. And again, we eliminate 3 to 4 because we can get to 4 from 1. And we keep going until we get the minimum spanning tree. So now, I believe, now we can get to all the nodes from 0, from any other node. And so we are done. And when the rest of the nodes are null, then we know we're done. So if you want to go online to this site and look at minimum spanning trees more, you can do that. Now there's an alternate algorithm that does the same thing as Prim's. It's called Kruskal's. So we list all the edges, and off to the right we list their weight. So edge 0, 1 has weight 6. Edge 0, 3 has weight 2. So we put them in just arbitrary order, whatever order we want. And then you sort them according to the weight. So here they are sorted according to the weight. 0, 3 has weight 2. 1 to 4 has weight 2. 1 to 6 has weight 4. 1 to 6 has weight 4. And we go down the list and include them until we find a cycle. So there's 0, 3, that's included. Now we go back to red being included. There's 1 to 4, it's included. 1 to 6 is included. We're just going down the list from the lowest edge to the highest. Now when we get to 0 to 2 and 6, 2 and 6 were in the set of vertices, but there was no current path between them. 2 and 6. Let me go back one. So in this situation, there is nothing that connects this part of the graph with this part of the graph. And so 2 and 6 has nothing between them. But now we don't need 0, 1 because we can already get to 1 from 0 or from any other node for that. Well, from 0. We can get to 1 from 0. So we include 2 to 5 because we can't get to 5. And then 3 to 4, we can already get to node 4 a roundabout way, but we can get there. And 4 to 5, same thing. So once again, here's a URL you can go to practice Kruskal. Okay, so in the next video, we're going to talk about, which probably won't happen until next week, we're going to talk about shortest path graphing, what you see on Google Maps, and also topological sorting.